Rico, but like the Dominican Republic. Politicians always talk about how important science and technology are for their countries. To quote the president, the last president, premier of China, the history of modernization is in essence a history of science and technology. Scientific discovery and technological inventions have brought new civilizations, modern industry, and the rise and fall of nations. And this is, from a Chinese perspective, very important. I firmly believe that science is the ultimate revolution. My president said the following: science is more essential for our prosperity, our security, our health, our environment, and the quality of life than it has ever been. All politicians say such words, but usually what they're talking about is technological invention, applied science, and addressing the very important concerns of society: health, environment, security, and so on. Technology-driven science is, of course, essential, especially in the modern economy. And the justification for investigating questions whose answers have ready applications to the problems of society is obvious. So there's no need to get up and talk so much about the importance of applied science. It is, as Chinese president said, as the American president said, essential in today's world. But basic science, why is it essential? What do I mean by basic science? Basic is not the best way of describing basic science. The best way, perhaps, is as curiosity-driven science. Science that addresses questions posed by nature. Research that follows the curiosity, that is driven by the curiosity of the researchers and not by the need to develop new products. What is the purpose of curiosity-driven science? My answer to this is threefold. First, obviously, to satisfy our curiosity. We, as a species, a young species, only 100,000 years old or so, evolved to understand and control the world around us. That's what makes us special, if anything, among the species of the earth. Our ability to understand and control nature. And the search for understanding the world around us and its origins are really at the core of what it is to be human. If you try to define, I believe, the true nature of what makes Homo sapiens special, it is this drive to understand, explain, and control the world. So the main reason we scientists work so hard to explore nature is that we're curious. We want to understand what the world is made of and how it works. and what the universe is made of and where we came from. That might seem a luxury to society. And basic science that explores the frontiers of knowledge might seem not as important as the immediate questions that face society. But even if you're not interested in answering those basic questions that nature poses, a society must support curiosity-driven science in order to motivate excellence. Young people are attracted, children ask these big questions. They're interested in what stars are made of, and what the history of the universe is, and what matter is made of, and how can we explain the forces that govern the world. And my experience is that most young children, young students, are attracted towards science because of those big and fascinating questions. Well, many of them then study science and learn that there are hundreds and thousands of more interesting questions, which are, in fact, much more practical. And most of them will go on to do applied science and technology. But unless a society, unless a country has a strong basis in curiosity-driven science, in basic science, those people will be lost to science and technology. And you'll have a country of people who work in service industries or lawyers and bankers completely. And the people who are driven to try to understand nature and do research will go elsewhere. The education that scientists receive attracts, as I said before, many of the most intelligent, inquisitive, innovative people to basic science, often to try to answer the big questions. But it benefits all of society by educating and training students who will enter the workforce not only in academic and scientific research, but as workers in many diverse industries. And finally, the argument for supporting and fostering curiosity-driven science is to produce new technology, new applications. If you don't understand new phenomena, you will not create new technology. This was said very well by a politician, not my favorite politician, Maggie Thatcher, who was a chemist before she became a politician. And she expressed this point of view very eloquently. She said, although basic science can have colossal economic rewards, they are unpredictable. Therefore, the rewards cannot be judged by immediate results. The greatest benefits of scientific research have always resulted from advances in fundamental knowledge rather than the search for specific applications. For example, transistors, which underlie modern technology, were not discovered by the entertainment industry, which now uses them, but by people working on quantum mechanics, wave mechanics, and solid-state physics. Nuclear energy was not discovered by oil companies with large budgets looking for new forms of energy, but by scientists like Einstein and Rutherford. Science is like a tree. I like to picture a healthy tree, a healthy balance between the roots and the structure, the trunk of the tree, which is the basic science. And a healthy tree has healthy branches and leaves and fruits. Why is it necessary to go through this route of curiosity-driven research that leads to new ideas, new insights, new understanding, and then new applications? I think the answer is very simple. Nature is much smarter than we are in posing good questions for research. Nature is much smarter than we are.
Yes.
And the questions it poses are, try to understand me, and you will gain new knowledge and new technology. If you try to bypass the understanding by immediately trying to solve an immediate problem, you are doomed to use old science and old technology. There's a famous story about Michael Faraday, who was, as you know, the Englishman experimentalist who discovered many of the properties of electricity and magnetism in the middle of the 19th century. The story is that Queen Victoria visited his laboratory and was shown all of these magnets and electrometers, and she was very impressed. She said, "Very interesting, sir, but what is it good for?" And Faraday famously said, "Ma'am, I don't know, but when we find out, you will tax it." Faraday had no idea what electricity and magnetism were good for. He had no idea that they would be used to create motors, radio, the whole Industrial Revolution. There's a similar story later, about almost 100 years ago, when the theory of quantum mechanics was developed in order to understand the strange properties of microscopic atomic structure, the structure of atoms. It was more or less finished in the year 1926 by people like Planck and Einstein and then Heisenberg and Bohr and Schrödinger, Dirac. They knew that this new, very strange quantum mechanics was necessary to explain the atom, but what would it be good for? They could not dream. But quantum mechanics now underlies all of modern technology, from the transistor to the integrated circuit to the laser and to all of these devices that now control our world. And this is just the beginning. The best is yet to come. I'm going to now discuss some of the questions that we are asking at the frontiers of science, at the frontiers of physics, since I'm a physicist. They're equally wonderful questions at the frontiers of biology. We now have the ability to control individual atoms, to observe and control matter at the atomic level. We can see atoms, pick them up, move them around, create new materials like graphene or nanotubes. We, in fact, have the ability to create novel materials that don't appear anywhere on Earth, atom by atom. And with increased understanding, perhaps, to construct materials with new properties and new uses. First comes the understanding, then the control, then the construction, and then we'll find a use, to be sure. What it is, I don't know. But we have yet, I believe, to explore all of the phases, the kinds of materials that can be constructed from the basic atomic constituents. One idea of how to use this is to construct what is called a quantum computer, a computer that is ruled by the laws of quantum mechanics instead of the laws of classical mechanics. Such a computer, if one could construct, would be much more powerful in doing many tasks than these incredibly powerful computers. And an enormous effort is being expended in order to understand the structure of matter well enough to create such a computer. My field is even farther removed from direct application. I, as Dr. Molina explained, have been studying the structure of the nucleus of atoms. And here in the latter part of the 20th century, enormous advances were made in identifying the basic constituents of the atom, electrons, and the basic constituents of the nuclei at the center of atoms, which are quarks. Protons and neutrons, which compose the nuclei of atoms, are made, we learned, of quarks. And we understood the forces that govern atoms and molecules and nuclei and quarks. The force of electromagnetism that Faraday studied, and the nuclear forces, which were finally understood in the 20th century. We have a very comprehensive theory of these forces called the Standard Model. It identifies the basic components of matter, the constituents of matter, the building blocks of matter, quarks and leptons, the electron, the neutrino, three families of such quarks and leptons, and it explains the forces that act on these particles. The last part of this theory you might have heard of, it's called the Higgs mechanism, predicting a particle which was famously discovered now almost 4 years ago in Geneva. This is an incredible achievement of basic science, a comprehensive theory, unbelievably successful. And you might ask, as Queen Victoria did, what is it good for?
What is it good for?
Well, like Michael Faraday, I don't know. But when we know, someone will tax it.
Tax it.
On the other hand, even before we know what this control and this understanding of microscopic physics is, we do know that the tools that scientists were forced to invent in order to study these phenomena have already had enormous impact. And economists have calculated that they have paid for this very expensive research many times over. For example, all modern forms of medical imaging had at their beginning detection devices constructed by physicists or chemists to study matter. This was the case at the very beginning of our study of the nucleus, that of the discovery of radioactivity. As soon as Röntgen, who by the way won the first Nobel Prize, discovered accidentally X-rays, within a few years people were using them to probe the inside of bodies. If you had left this to politicians to figure out, have a crash program, how would we see inside a human body? They probably would have constructed bigger and bigger flashlights. MRI, which is now the modern form of studying what goes on inside a body, and saves millions of lives a year, was discovered, was a consequence of physicists trying to understand the magnetic properties of nucleons, of protons. That was they invented a technique which was, upon invention, some few years later, realized could be used to image the molecule, the protons inside the nucleons of atoms anywhere in the body. The tools used to carry out the research can be employed in surprising, unanticipated general applications. That's again because when we ask questions posed by nature, we're forced to come up with new ideas, new ways of studying nature that are well guided because the problems are ones that are posed by nature. Some other examples are the development of parallel computing. In order to do things like solve the theory of the strong nuclear force that we got the Nobel Prize for. That's a theory allows you to calculate the masses of all these particles that we see in the world or produce in accelerators. But doing so requires massive computations, and one of the leaders of pushing that technology, that software forward, was theoretical physics. But it has applications now in weather forecasting, hedge funds, market trend analysis. Particle accelerators that we use to smash particles together have now become a multi-billion-dollar industry. Especially synchrotrons, which are used to study materials, biological cells, and treat disease. And finally, the example that is probably not so well known is something you might have heard of called the World Wide Web. The World Wide Web was developed by physicists working at CERN who wanted to communicate in their international collaboration among groups that were all over the world, send out data, discuss the data, analyze the data, and they invented the World Wide Web. They didn't patent it, which is why it is so open and free. And it led to the modern IT revolution. My field of particle physics is now becoming related to another field, that of astrophysics and cosmology. Since astronomers looking at the universe as a whole have discovered two other forms of energy and matter we call dark matter, which is some kind of heavy particle that doesn't interact strongly with us, and dark energy, which causes the universe to accelerate its expansion. And that poses to us, physicists, two fundamental problems that partially guide our current research. What is the nature of dark matter? Can we produce it? Can we detect it? What is the nature of dark energy? We also have this grand theory, the standard model, the standard theory, but the forces that act within the atom and the nucleus, if you were to look at them at very short distances, very, very short, we believe they would unify into one force. In fact, they appear to unify together with the fourth force of nature, that which you all know, gravity, that makes planets go around the sun and keeps you in your chair. At these frontiers, we are asking very interesting questions of nature. We're asking questions like, does space have extra quantum dimensions, something called superspace, and a new symmetry called supersymmetry, which we hope to discover at the largest of our microscopes that can probe to distances which are 100th of a billionth of a billionth of a meter. I call that nanophysics. That's what is being explored at the Large Hadron Collider, an international collaboration involving most nations in the world, 20 kilometers around the ring, 200 kilometers underground. Around this ring, protons travel at almost the velocity of light between Switzerland and France. They collide, they produce lots of particles. We analyze what happens in those collisions to understand what quarks perhaps are made of. And one of the ideas that was referred to by Dr. Molina, that I worked on for many years, is string theory. That the basic particles in nature, the quarks, the electron, are all different vibrations of a single extended object, like a string, like a violin string that can have many different harmonic, many different modes of vibration. It appears that all of the particles that we've ever observed and the forces can be contained in the theory of a single vibrating string. But that's still speculation. And we have other interesting speculations. For example, it's possible that space has extra dimensions. In other words, each point, this point right here, is not really a point. If I were to look with a very good microscope, I would see internal directions I could move. But they're so curled up, small distance, that I can't see it with current microscopes, current accelerators. So we don't know. We don't even know what space and time really are. Space and time, I remind you, are not something you feel. They're something that we invent in the first year of our lives to understand the world and control it. We know that if we look at the nature of space as a description of physical reality at very short distances, with our current theory, it becomes very uncertain space-time foam, and what we suspect that space and time itself is an emergent, approximate concept, good perhaps, good indeed for describing large stuff, but at very short scales. It's made of something, and we explore what is space-time made of.
It's a really good question.
And recently, you all have heard, I'm sure, that in our studies of gravity, we have now finally confirmation, if we needed it, we were sure, but confirmation, another confirmation of Einstein's theory by observing directly gravitational waves. Einstein's theory of gravity, which is that gravity has to do with the dynamics of space-time, requires that gravity propagates from the sun to the earth with the velocity of light. That if you shake the sun, you set up a disturbance in space-time that propagates to the earth with the velocity of light. And people, LIGO, has used interferometers, one in Louisiana and one in Washington, to look for waves that distort space, change the length of the interferometer, and would allow you to see waves of gravity. And after 40 years of constructing and improving at a cost of almost $1 billion, a few months ago, they observed what appears to be the collision of two massive black holes, 1.3 billion light years away. We don't know exactly which direction because we only had two observatories. Both observed that there was a wave of gravity passing through them for less than a second, which appeared to describe